I'm Saharon Rosset from Tel Aviv University, and this is a tutorial on EM, on expectation maximization. It's always a challenge giving a short tutorial, especially to a heterogeneous audience, so people don't fall asleep because they know it and it's boring, and they don't fall asleep because it's too technical and they have no idea what I'm talking about. So we'll see how successful we are in engaging one or both of the audiences. But for those who are going to fall asleep, so basically, maybe the main message of my talk is this notion that EM really can be thought of as we want to do maximum likelihood, and we're going to use basically a minorization maximization trick to do maximum likelihood. So really, we'll start by making sure we are clear on what is maximum likelihood and what is minorization maximization, and then we'll talk about how together they come to give us EM algorithms. Okay, so maximum likelihood, we all know what it is, but sometimes maybe it's actually more complicated than it seems, and the main sort of conceptual issue with maximum likelihood is that we have this function which depends on parameters and depends on data. And really the proper way to think about this function, this distribution of the data or the probability of the data is as a function that has parameters and is a function of the data we see. But when we want to think of it as a likelihood function and maximize it, we actually change our view. And the same function, we now look at it as a function of the parameters themselves. Okay, so even though really in the world we imagine there's some distribution, some parameters, and data is generated, or we get data by drawing from that model, so that standard view is really the view of how we think of the world as working. When we do maximum likelihood, we just take the same function and we now look at it as a function of the parameters, meaning we now imagine that the data is somehow fixed, it's already given to us, and we are just interested in how this function changes when we change the parameters. Right, so this is maybe a conceptual leap that sometimes is a bit difficult. But given that, we know exactly what maximum likelihood is. Maximum likelihood is find the value of the parameters that maximize this likelihood function. Now, by the way, theta, in everything we do, we don't really differentiate between vectors and scalars. So we generally assume that theta could be many parameters. A vector of parameters could be high dimensional even. But the maximum likelihood problem is maximizing this likelihood function, or equivalently maximizing the log of the likelihood function. Why is it equivalent? Because log is a monotone transformation, so the maximum, the argmax, which we are interested in, the parameters at which the maximum is attained, is the same solution. So here's a very sort of generic view. We have the likelihood function, and we're looking for the maximum, but we are really not looking for the maximum, we're looking for the argmaximum. Right? And our interpretation of maximum likelihood is this is the value of the parameter which most fits our data or makes our data most likely when we look at it as a function of the parameters. Okay, so this is stuff hopefully we all know. What is minorization maximization? Hopefully we've all heard of that as well. But so now let's forget about maximum likelihood and think about a completely generic situation where we have some function and we want to find an extremum, say maximize the function. So the trick is we're going to find a separate family of function, g of x. Now we index the same family of function by x. And what this family of functions is going to have is this set of nice properties. So gx at the value x is equal to f at the value x. So actually when I choose x, I choose the member of the family which exactly complies with this requirement. The second requirement is that g is completely under y. So at this point, at x they are equal. At any other point, g is under y. And to make all of this make sense, gx, or for any member of this family gx, is a function that's easier to optimize. Okay, so if you give me a function gx, I can easily find its maximum for this purpose. And from these properties, it is already guaranteed that, in fact, I can climb up f. I'm trying to get to a maximum of f. So this is guaranteed that I can climb up f. Why? I start from some current guess xt, and then I look at this function g that's defined by this point that I currently have. Then I maximize it. Now it's easy to see this sequence of inequalities. Some of them might be weak inequalities, but let's assume they are strong inequalities. So because g is under f, then at this maximum point I found, f is bigger than g. Because I maximize g, g at the new point is bigger than g at the old point. And from the first assumption, that's equal to f at the old point. And we can see it visually very nicely. So I start here at x1. Here's my f. Here is my nicely behaved function g. So I choose g that is tangent to f at the point, at my first point. Then I maximize g. I know, what do I know? I know that I've increased g of x1. I know I'm under f of x at this point. So I can now define this point x2. And the fact that I'm higher than I was is the thing that this entire thing guarantees. And I can keep climbing up f, right? So that's nice because it's a super general recipe, and it's actually useful in many different situations when I have complicated functions that I want to optimize, as long as I can find these surrogates, these minorizing functions. Okay, so what does this have to do with EM? I'm going to introduce EM as people are used to seeing it in a little while, but if we understand these two ideas of what is maximum likelihood and what is maximization minorization, then basically we understand what EM does, at least from the mathematical perspective. We still maybe have an interesting statistical perspective that we're going to look at. So we want to do maximum likelihood estimation over some parameter space. And what EM gives us is actually a way of defining MM algorithm. Actually, MM algorithms, we can define many different MM algorithms through the EM mechanism. So it's a way to define the family GX of functions that we're going to minorize our likelihood with. Okay? Okay, so now if we understand that, we just have to go through the formalities of the MM mechanism, and we have an algorithm that monotonically increases the log likelihood. We can say more than that in general about MM algorithms under mild assumptions. Because the minorizing function is tangent, then we know that to first order we're increasing the same rate as f. So under all kinds of relatively mild assumptions on derivatives, it means not only that we go up, but that we're actually going to converge to a local optimum. And by the way, why is it not obvious from first sight that we converge to a local optimum? Because if we're going up the function, yeah, like Achilles and the hare, we might be going at a slower and slower rate, and we might actually stop at a point that is not even a local optimum. But because of the gradients calculations, we can generally guarantee that we're going to go up until we reach a local optimum. Of course, if the likelihood or log likelihood function is not unimodal, not even a question of convexity, it might have many local optima, then there's no guarantee of convergence to the global optimum. Okay, so this is the MM perspective. Now, maybe it's a good time to step back and talk about EM maybe as people are more used to it. So again, we have some log likelihood function. And what does it mean that we have a log likelihood function? We have data, and we have a parametric model that describes the probability of the data as a function of the parameters, and we now look at it as a function of the parameters and not as a function of the data. And the trick we're going to do, the main EM trick, is that we're now going to imagine that we have some more data that we actually don't have. But we can write what the likelihood would look like if we had the complete data, if we had the data we have and also other data that we don't actually have. And now what we're going to do with this log likelihood, with this LC, which is the complete log likelihood. So I try to make sure that I write in red the things where the places where we play pretend. So we play pretend is like we pretend we have more data. So that gives us this complete likelihood that we would have if we had the other data as well. So what we're going to be doing in an EM algorithm, in the E step, we're going to calculate the expected value of this complete likelihood. And why do I need to calculate an expected value? Because what I see, in fact, is only X. I don't see Y. So I need to calculate the expected value of this thing given what I actually see, which is X, because I don't see Y. So I basically integrate out what I don't know, which is Y. So far it seems like a pretty not necessarily smart thing to do, because I imagined I have something that I don't have. Now I have to somehow solve the fact that I don't have it. So I calculate this expectation. Then once I calculate this expectation, I once again get a function that does not depend on Y. It's a different function. It's the expected value of the complete log likelihood. Now I maximize this function. Okay, and it turns out that in many cases, like the examples we see, it's much easier to maximize this function, which is the expectation of the complete log likelihood, than directly maximize the likelihood function we want. Okay, so this is actually an MM algorithm for maximizing the original function, and this is an important point that I think is often missed. The whole time what we're trying to do is do maximum likelihood on our original problem, right? Everything we're doing with imagining we have more data and so on is just a way of optimizing our original. I know that because I taught EM in detail, and they gave a question in the exam, and more than half the students think we are actually maximizing the complete likelihood. But we can't maximize the complete likelihood because we don't actually have the data for the complete likelihood. We are maximizing the likelihood of the data we do have. Okay, so let's run through an example, the most basic classroom example, and we'll try to do it in a way that will hopefully be somewhat instructive. So our problem setting is that our data is an IID sample of d-dimensional observations, right? So I have n d-dimensional vectors, and the model that generated this vector is a mixture of Gaussians. And maybe we'll start with a picture. So here we have actually two Gaussians, one centered at the origin at 0, 0, and one centered at 3, 3. And the one at 0, 0 has 70% of the observation, and the one at 3, 3 has 30% of the observations. So this is, if I generate, so this is in 2 dimensions, right? So this is what my data looks like, right? So so I have this data, and now I can look at the likelihood model for my data. So if I have some parameters, and the parameters here are what? The parameters in this model are how much probability is in which one of the Gaussians, and then the parameters of each one of the Gaussians. So I have these probabilities over the Gaussians, the means of the Gaussians. So these are k parameters, or k minus 1 because they need to sum to 1. These are kd parameters, the k times d parameters, and this is like k times d square parameters. So there's a whole bunch of parameters here in this problem. But given all the parameters, I just say each observation, there's some probability that it belongs to each one of the clusters, and then just the multivariate Gaussian density for the chosen cluster, right? So this basically is the marginal density, and that's really the density from which, from which the data I have here is drawn. This is an accurate description of the density of points in this picture. Okay. And our maximum likelihood problem is given the data I have. I want to maximize this function. This is just for one point, so, and they are independent, so I have to multiply them. I may want to do log or not, it doesn't matter. So this is the log likelihood. Maximizing the log likelihood is my maximum likelihood problem. Okay, so, actually I already showed you the example we're going to follow is going to, so we can draw things and we don't have too many parameters flying around. We're going to have just 2 dimensions, 2 clusters, or 2 Gaussians, and a known covariance matrix. So actually here, in this case, we have just 1 parameter here because the other one is 1 minus, and 4 parameters here, and no parameters here because we know the covariance. Okay. So now we can see this data. This is X. This is the data we see, right? And there's a very natural notion of Y here, data we don't see, which is which cluster or which Gaussian each data point came from. When we see the data, we do not know which Gaussian each data point came from. Okay, so I'm going to define it, sorry. So here's the next step. The data that we would love to see, but we don't see, is actually which Gaussian each data point came from. Okay. So before that, maybe write down the log likelihood for our simple case with just 2 clusters in 2 dimensions, or the important point is that it's just 2 clusters. So the likelihood is the probability that I come from the first cluster times the likelihood in case I'm from the first one, plus the probability I come from the second one times the density in case I'm from the second one. And the key point is that this has like sum inside log inside sum, but inside sum, the last one is not a problem, but having a sum inside the log automatically makes this a function that's very difficult to optimize. For example, calculate derivative. So the trick we're going to do is we're going to define unobserved data, which will be for each observation, whether it comes from component 1 or from Gaussian 1 or from Gaussian 2. Okay, so in this case, I defined it as the indicator that you come from Gaussian 2. So it's 1 if you are from 2 and 0 if you are from 1. Now this very much immediately simplifies the log likelihood if we want to write the complete log likelihood, right? Because the complete log likelihood knows which Gaussian you come from. So basically, I just have to account for the fact that the Gaussians have different probabilities and then the density of the Gaussian. So yeah, so this log, because there's no sum in the log, I can now break the log of the product into sum of logs. Okay, so this is a nice friendly function that's very easy to optimize if I want to optimize it, but I'm not going to be able to optimize it because I actually don't observe the yi's. Okay, so now I've added to my plot the much nicer plot I would like to have with the y indicators in the, and for example, everybody knows that if I knew the y indicators, maximum likelihood would just be to average the observations in each cluster separately, and I could calculate the covariance matrices easily and so on. Okay. And I've also marked here the centers of the 2 Gaussians of the 2 clusters. Okay, but we don't observe the unobserved data, so we're going to design an EM algorithm for this. So in the E step, we need to calculate this expectation of the complete likelihood, given the data we see, and of course the current parameter estimates. We need parameters to estimate these conditional expectations, so we're going to use the current parameter estimates. If we want to calculate this expectation, then basically it means that we have to look at this this complete likelihood and just calculate the expectations of the things we don't know. So here we use the indicator functions, but in case we don't know them, we have to calculate the expectation. Expectation of indicator function is a probability. So basically this says if the indicator function is 1, this is my likelihood, and if it's 0, this is my likelihood, and if it's 1, this is my likelihood, meaning the expectation is the probability it will be 0 times the likelihood I would get if it was 0, and plus the probability it would be 1 times the likelihood I would get if it was 1. So basically all I have to do is calculate these conditional expectations. And conditional expectations are easy to calculate because we have Bayes' theorem. So a conditional expectation is basically, or a conditional probability, sorry, is basically the joint over the marginal. So here's an explicit expression for this conditional expectation. And notice that here all the parameters are the current estimates, right? Because this is, so one thing we have to notice is that our parameters sort of appear in two different roles in this expression, right? So my current parameter estimates appear in calculating these expectations or probabilities. And my real parameters, the ones I'm trying to estimate, appear within the likelihood expression itself. Okay, so this is the E step. What I ended up with is an explicit expression for what I need, this expectation. It's explicit in the sense that I know exactly what these red functions look like. I have them here. So I have everything explicitly. I have my E step function. What do I do in the M step? In the M step, I'm now going to maximize this function. Okay, so this is, again, is a function of the parameters, and I want to maximize it. And in this case, it actually turns out to be very simple. So here's the closed form expression for the next step of the function. And when I say yt, this should be yit. When I say yt, I mean the expected value I just calculated, right? So there's closed form, given these expected values, there's simple closed form solution to the EM, to the M step of the EM. And basically, I've said everything I need to fully specify an EM algorithm for this problem. So we remind ourselves of the data we had. This is the observed data. This is with the unobserved data. And now we can follow the EM algorithm iterations on this data. So we start at iteration 0 from a completely random assignment of the data points to two clusters, to two Gaussians. Or actually what we do is we do we don't need to assign points to clusters. We need to give a probability for each point, or a level of allocation of each point to each Gaussian. So we start from random. We see that after iteration 1, what we have is not completely random, but looks nothing like the true model that generated the data. And as we move forward in the iteration, simply alternating the E and the M steps. After 10 iterations, we see that we've largely separated the points correctly by the Gaussians, and nothing much changes from that point on. And notice that we do not only have, so what do we have here? What we have here is the scale that allocations that are close to one Gaussian are blue, and ones that are close to the other, that are almost fully or 100% allocated to the other, are in red. But we have this range in the middle. And of course, when we do the EM, when we don't actually know the original identities of the Gaussians, this is a very easy problem. So most of the points are very confidently identified as belonging either to the Gaussian at 3, 3 or the Gaussian at 0, 0. But we still have some points in the middle that, of course, the yits are not 0 or 1, but are probabilities in between. So, so this is just to show that, at least on this simple example, EM works very well, quickly, and basically recovers the correct model. One point that maybe should be noted here, that EM for this problem and k-means for this problem are not the same algorithm, and specifically k-means is not an EM algorithm, or we can say it is an EM algorithm if we assume 0 or infinitesimal variances for the two classes, but that's not really an interesting probabilistic model. So we can think, at least from a statistical perspective, we can think of EM for this problem as sort of an improved version of k-means that's a bit more complex. Okay, so this is what I wanted to say about the Gaussian mixture example. And how all of this is connected to minorization maximization. Hopefully it's clear, but basically we can show that the result of the E-step is this function, the expected value of the complete likelihood given the observed data, and that basically minorizes the observed data at the current point. Okay, so this is exactly a minorization maximization algorithm, and the way to minorize is to calculate this E-step result. And the obvious conclusion is that EM is an MM approach for the specific problem of maximizing the likelihood. This is a minorization maximization approach. Okay, I have some more time, so let's talk about more interesting or maybe very well known, but maybe less first-year example of the use of EM. And this is for PET, positron emission tomography imaging. So what we have in PET is basically this very schematic view. In the middle is the tissue or the image, and it's divided into voxels. I mean, this is 2D, so it would be pixels, but in fact it's 3D and it's voxels. And around the tissue we have sensors, so that these green dots signify sensors. And what happens is that when we do the imaging, we have events happening in each one of the voxels at each one of the points, but let's say discrete voxels. So at each one of the voxels, some events are happening, and there's some Poisson rate at which they're happening. And the fact that this is Poisson is physics. There's no doubt that this has a Poisson distribution. And what happens when an event happens is that actually two particles shoot in opposite 180 degrees to each other. And so what actually we see is the two sensors. They don't have to be 180 degrees from each other because the event could happen here, and so the two sensors could be here. But there's two sensors that simultaneously sense something. Then we know that an event has happened somewhere on the line connecting the two sensors. We don't know where. Modern machines think that they somehow know where. How would they actually know where? If we're able to measure time accurately enough so that the difference in flight time from flying to that sensor and this sensor can be measured accurately, then just based on inverting the speed of light, we can calculate where the event happened. But traditionally, we don't have that time sensitivity, so we just see that at the same time, up to our granularity, we saw something in two different sensors, and then we know that the event happened on the line connecting the two sensors. And this is called an incident, when two sensors simultaneously sense the event, and it happened somewhere on the line. And so we can easily see that this actually gives us a simple Poisson regression model, that what we observe are those incidents, events that we see. But because we don't know where they happened, we have this matrix A, which transforms from the events in the voxels to the incidents we see on the lines. It basically integrates over lines in the picture, right? So we have a situation where the parameters we're interested in are those lambda. What's lambda? Lambda is sort of the concentration of material in usually sugar in each one of the voxels. And we get to observe something that's Poisson distributed, but not the actual Poissons that happen in the voxels, but after the transformation to the lines. Okay, so yeah, so lambda is the sugar concentration in each voxel. So lambda is this very long vector. These are the parameters that we want to estimate because this is actually the image we're trying to get. A is this huge, very complicated, but basically physics-based, so known matrix that transforms from the events happening in the voxels to where we see them. And so if we wanted to find a maximum likelihood estimator, this is just a Poisson regression, where the Poisson means of the data we observe are linear transformation, multiplication by this matrix A of the parameters we actually want. And this has an identity link for those who know about GLM. So this is kind of non-standard GLM to have identity and not log link. But the physics tells us this is Poisson regression with identity link. And it turns out that if we just wanted to ask R or Python to do GLM on this, that would not work. And basically the reason it would not work is the problem is too big. The number of voxels, say, is on the order of 100,000, but the dimension of X is much bigger because X is pairs of sensors. So the dimension of X, the number of observations we have, is how many pairs of sensors we have. So this is really a huge problem. So the matrix A, I mean, we can calculate it, but we cannot really write. We cannot even write the matrix A. It's too big to write. Okay. So there's a wonderful example of where statisticians really had an impact in the real world, and specifically EM had impact in the real world. These Shepp and Vardi, two well-known statisticians, and they came up with this in the 80s that you can actually do this efficiently using an EM algorithm. And the key here is what's the unobserved data. There's very natural unobserved data. The natural unobserved data is how many events happened in each one of the voxels, right? So we want the Poisson rate of each one of the voxels, but there's also unobserved data, which is how many events actually happened in each one of the voxels. So it's very natural to make this the unobserved data, because once we observe this data, then the complete likelihood doesn't depend on X, doesn't depend on our observed data, actually. So this is a nice example where, given the unobserved data, the likelihood actually doesn't contain the observed data at all. So it's just a simple Poisson likelihood of the unobserved data. So we can follow, we don't have time for that, but we could in principle follow the E and M steps of this and see that we end up with this very nice and simple updating formula. So this is what Shepp and Vardi did. And a lot of this is about the wonderful properties of Poisson, that when you do linear combinations of Poisson are Poisson, and then Poisson conditional on sums of Poissons has a binomial distribution. There's all kinds of things that are really important for doing statistical things with Poisson. And it turns out that the EM algorithm boils down to this very simple updating formula. This is a formula that someone could come up with as just an intuitive iterative algorithm, and it would be fine, and it would work. But this is actually a formal EM algorithm for this problem. So what do? We look at the actual number we observed on each pair of sensors. We look at the vector. So this is a very long vector of how many incidents happened on each pair. We compare it to the expectation under the current parameter estimates, right? This is this ratio, observed to expected. We multiply that by this by the column of A, which allocates events from each voxel to each pair of. So this is saying this is like weighting, and this is a different type of weighting, and this product, this inner product, is the update to the jth. So I mean, it requires some thinking about the dimensions and the linear algebra, but it is basically what someone who sat maybe a long time and thought about how to intuitively update parameters, they may well come up with that. And this was done in the 80s. And many things have happened in PET since, but to a large extent, this is still what people use today in PET. The main exception is what I told you about. It's called time of flight. When I have time of flight data, then I don't need to do all of this because I know where everything happened exactly. But other than that, this is still what people are using for PET reconstruction. Okay, so to summarize, so what's good about EM? That it tends to be computationally efficient. In principle, this can be applied in any maximum likelihood estimation problem. The key, of course, is coming up with sensible and relevant missing data model or unobserved data model. And if we come up with a good unobserved data model, then we also gain the interpretability like we had in the Gaussian mixture problem, where we actually interpret these conditional expectations as the cluster allocations for our model. So we should if we think of Gaussian mixture model as a clustering approach, then that really illustrates how the missing data model or the unobserved data model is really super informative in itself about our problem. And if we think about the challenges in EM, so one thing that maybe we should keep in mind is this common misconception that the moment we do an iterative algorithm like k-means, we're doing an EM algorithm, which is not true. An EM algorithm is this formal framework that has missing data and calculating expectations. And while we sort of have guarantees on convergence to a local optimum, there's no general theory on how quickly this is going to happen. We saw in the Gaussian mixture example that it happened very quickly. And in the PET example, this algorithm is much more efficient than anyone else could come. Say first order gradient descent algorithms. We can think of this as sort of being a second order algorithm at the cost of a first order algorithm, right? Because we get this function. As long as the minorizing function is locally similar enough to the function we're trying to estimate, then we're kind of making second order steps and not first order steps. Okay, thank you.